All right, y'all, let's get started. We got one more topic to finish to button up chapter 18 here. This is what's called a solubility product, KSP, okay? So to introduce this, let me remind you all of a type of reaction that you discussed last semester, what was called a precipitation reaction. Okay, so if we take a solution of sodium chloride and we mix it with a solution of silver nitrate, okay, we will get a, this really favors the products. We will get a solution of sodium nitrate. All right, but then interestingly, we will get a precipitate that forms out of this solid silver chloride. All right, so these are these precipitation reactions. You did a few of these in lab. If you remember, you took these two clear colorless solutions and you mixed them together and you got like this milky white chunky substance at the end, right? That solid precipitate that formed in that test tube, okay? So the way that these experiments work is you take a soluble ionic compound, you mix it with another soluble ionic compound, all right, and importantly, one of your products that you get is insoluble. All right, that's why it precipitates out. That's why it's that solid precipitate. So these words, just to be clear, soluble means it will dissolve in water. Insoluble means it will not dissolve in water. All right, and at that point in your chemistry careers, the world was all like black and white in terms of how these ionic compounds were divided up. They were either in the soluble bin or the insoluble bin, right? Everything was sort of neatly divided into this binary. Well, it turns out that it's not quite that simple. It's a little bit more of a spectrum type of concept. In particular, there is no such thing as an ionic compound that is truly 100% insoluble. Okay? That concept of insoluble is a little bit of a lie. Every ionic compound will dissolve to some extent in water. Maybe only a teeny, teeny, tiny amount, right? But nothing is truly 100% insoluble. So that's what we're going to be building off of today. We're going to take this insoluble compound here, and we're going to figure out just how much of it will actually dissolve in water. And you know, punchline, it's not going to be very much. It's going to be a very small amount, but it's not going to be zero. Okay, that's how that's these solubility product problems here. So again, just to summarize, no ionic compound is truly 100% insoluble. They will always dissolve to some extent. And it's going to be minor, but nonetheless. Okay, so let's say if 10 grams of silver chloride is added to water, what is the concentration of silver ions that will dissolve? Okay, so we got this compound that previously we had sort of treated as 100% insoluble, but that's a lie. We're going to take this silver chloride, we're going to put it in water, and we want to figure out just how much of it dissolves, right? What's the concentration of silver ions that I get at the end? All right, so one of the things that before we move on here that I want you to keep in mind are that these are just going to be equilibrium problems, all right? These are not going to be the 40-hour titration type problems. They're really extensive like that. This is just based on this equilibrium chapter that we learned. All right. The very first thing that we need is what we're going to call our KSP reaction. What reaction are we talking about here? All right, similar to like our Ka reactions, our Kb reactions, they're all going to take the same similar form. All right, we're going to take our insoluble compound. In this case, it was silver chloride. All right, starts out as a solid. We're going to put it in water, which will then have it dissociate into its two ionic components. In this case, the silver ion and the chloride ion. All right, so on our left-hand side here, our reactant is always going to be this insoluble solid ionic compound. And on our product side will be the aqueous cation and the aqueous anion. Okay. Now, similar to when we were talking about like weak acids and weak bases, we're making a solution here, right? So why don't I have water that appears in this chemical reaction? Okay. Because when you take an ionic compound and you dissolve it into water, yes, that water is important. It's interacting with these ions. But there's no chemical bonds that are being broken in a water molecule or made in a water molecule. The water's not actually involved in the bond making and breaking, which is what our chemical reactions summarize. Right? So if I included water over here, I would just also have it over here, and we cancel things that appear on both sides, right? So water's not consumed in a reaction when you are dissolving a salt in water, and that is not the case when you take an acid or a base and you mix it with water. Water is then involved in the chemistry of those compounds, all right? So let's just note here, water does not appear in our KSP reactions, which is different from our Ka and Kb reactions, all right? All we have is our insoluble solid ionic compound on our reactant side and our aqueous cation and anion on our product side. Okay? And like always, our chemical equations, it would be important to balance it. This is a fairly easy one because it is a one-to-one reaction, right? So everything's all balanced here. But that would be another step we would do for our KSP reactions. Okay? So then we're going to build our equilibrium expression. Right? Everybody take a second. Given our balanced chemical equation here, build me the equilibrium expression for this reaction. Again, these are just going to be equilibrium problems. All right, so I'm going to take my products over my reactants. So my product is the silver ion and the chloride ion, but I'm not going to include that over the reactant portion because this is a solid, so I don't have to include that in my equilibrium expression. All right, so I just have a product of these two ions that I get at the end. All right. And then just like before, for our KSPs, we have on our constants page a list of a bunch of different equilibrium constants for these particular reactions. Right? So you would look up your compounds. So in this case, we were talking about silver chlorides. Let's go over here to the silvers. I'm going to look up silver chloride, and I get a KSP value of 1.77 times 10 to the negative 10. Right? So just like our Kas and our Kbs, just like all equilibrium constants, these are tabulated, and that's an addition to our constants page that we have. All right, so 1.77 times 10 to the negative 10. Cool. Let's just make note of that. All right, so before we move on here, is this equilibrium constant a constant that favors the product side or the reactant side of our reaction here? Reactants, right? And that checks out because, again, these are relatively insoluble compounds. We're going to get very little of our product that's formed here. And so in general, you look at these KSP values, they are all pretty tiny numbers. Some of them are ridiculously tiny numbers. 10 to the negative 54 is like a ridiculously small number, right? So all of our KSP values are going to be very low because these reactions don't favor the product side. They, in fact, favor the reactant side. So that checks out. All right, and then in order to finish this problem off here, how do we think we're going to fill in our KSP expression? What are we going to do? Ice table. Absolutely. All right, so we're talking about this reaction here, so I'm going to build an ice table. All right, we're not changing our volume at all, right? So I can just talk in terms of concentration. I don't have to put it in moles. All right, now, this is one of the more bizarre aspects of these problems here. And I mean, you can convince yourself of it pretty easily looking at our KSP expression. But I'm told that I'm starting out with these 10 grams of silver chloride, right? But my concentration of silver chloride is not going to factor into my KSP expression at all, right? It's a solid. Talking about the concentration doesn't even really make sense. So we do not have to keep track of our initial amount of our solid. This calculation would be the same if we started out with 10 grams, 10 milligrams, or 10 kilograms, right? It doesn't matter how much solid you start out with. You always get the same concentration of ion here. And again, it's going to be a really tiny number. All right, so we don't have to keep that 10 grams as kind of a red herring here. We don't have to worry about that at all. We just need to say, all right, we don't have any of our ions to start out with. Are these ions going to go up in concentration or down in concentration? Are they products or reactants? They're products. Do products go up or down? They go up. All right, and then 0 plus x is x. 0 plus x is x. All right, so then I'm going to take these values and plug them back into my equilibrium expression. X is the concentration of silver. X is the concentration of chloride. So I get my KSP equals x squared. And again, that's that 1.77 times 10 to the negative 10 value that we looked up. All right, so if I solve for x here, I'm just going to take the square root of the 1.77 times 10 to the negative 10. All right, x equals 1.330 times 10 to the negative 5. I'm going to just randomly keep 3 decimal places on there. Okay? And so we get a small number, right? There's only a very small amount of this silver ion that, well, I guess real quick, let's just do a sanity check here. We got X, right? Are we done? What are we being asked for? What is the concentration of silver ions? So we got X here. Are we done? Do we have the concentration of silver ions? Yeah, we're done, right? In this case, X is the concentration of silver ions, so I'm good. All right? So, cool. We have our concentration of silver. Again, my point is, you get done with the algebra, go back and check your ICE table. Make sure to check what it is that you just solved for. All right? So, this is not a big number, right? But it's also not 0. And that's the whole shtick here, is this is not a very soluble compound. There's only going to be a small quantity of these ions that dissolve in solution. But again, it's not 0, right? Small number is different than 0. All right. Finish this off here. What are the units on this number? Big M, molarity. All right. Talking about a concentration, that would be in units of molarity. Okay, so now let's just do another one from scratch here. So we're going to put 10 grams of cadmium hydroxide into water. And we want to know what is the concentration of cadmium ions and what is the concentration of hydroxide ions. All right, so first step, give me that KSP reaction for our cadmium hydroxide in water. All right, so I'm going to start off with my solid cadmium hydroxide on my reactant side. This is going to dissociate into cadmium ions, which are aqueous, and hydroxide ions, which are aqueous. And then I'm going to need to make sure to balance this chemical equation here. For every 1 cadmium hydroxide that dissociates, I get 1 cadmium, but I get 2 hydroxide ions. All right, now, just to remind you all, hydroxide is one of these polyatomic ions like sulfate or phosphate. That is my anion, right? This compound is not going to dissolve into oxygens and hydrogens and cadmiums. That polyatomic ion does not split up. That OH is my anion, right? So I didn't break up this OH here. It is my polyatomic ion. And if we look on our table, we see a few of these, right? We have phosphates, we got sulfates places, I'm sure, whatever this thing is, an iodate. Here's a sulfate. All right, so just beware of those polyatomic ions. Those are not going to break up. Those are your anions. All right, and get rid of this. Cool. So now that we have our KSP reaction, give me my KSP expression. All right, so again, products over reactants, but my reactant is a solid, so I don't have to include that. I have my cadmium ion concentration times my hydroxide ion concentration. All right. It's been a minute since we've dealt with chemical reactions that weren't just simply one-to-one, right? All of those acid-base reactions were always one-to-one. This is not the case here. I have this coefficient of 2. And remember, when we're building our equilibrium expressions, these coefficients become exponents. All right, so that hydroxide ion concentration is going to be squared in my KSP expression. All right, and then lastly, we need our ice table. All right, and again, yes, it said that I started out with these 10 grams of our cadmium hydroxide, but again, we don't have to keep track of that initial amount at all, right? That doesn't appear in our equilibrium expression. The only thing we care about are these ions, right? At first, I don't have any of them dissolved in solution, okay? They're the products of this reaction, so their concentration's going to go up, right? But again, it's been a minute since we've dealt with these reactions that aren't one-to-one. So remember, your stoichiometric coefficient is going to appear in your change box as well. For every 1 cadmium ion that's formed, I get 2 hydroxide ions. All right, so then we sum everything up. 0 plus x is x. 0 plus 2x is 2x. We're going to plug this back into our equilibrium expression. X is our concentration of cadmium. 2x is our concentration of hydroxide. Okay, let me make some room for myself. All right, so importantly, when we fill this in, this is a very easy mistake to make. My KSP is going to be x times, in parentheses, 2x squared. Right? That concentration of hydroxide, that 2x, is squared in my equilibrium expression. The bottom line is that that exponent has to hit both the x and the 2. Right? So I'm going to put it in parentheses. Okay, so this would simplify to 4x cubed. All right, so then lastly, in order to finish this off here, I got to look up that KSP value for this particular compound. So go to my table. We'll look under our cadmiums here. Cadmium hydroxide has a KSP of 7.2 times 10 to the negative 15. All right, so then in order to do my algebra here, I'm going to divide both sides by 4. And I'll cancel that out over here. All right, and then I'm going to need to take a cubed root of this number here. So everybody make sure, let's take out our calculators and make sure that we can take higher order roots here. Okay, so you may have a button that looks like this where you can fill in that value. Okay, the other thing that also always works, and this is a sort of an algebra thing, and this isn't an algebra class, so I don't want to get too far into it. But if we take that 7.2 times 10 to the negative 15 divided by 4, we can also raise it to the power of 1/3. That's the same thing as taking a cubed root. And so what we get, x equals 1.216 times 10 to the negative 5. Okay, so again, make sure that you can take those higher order roots. If anybody's having trouble with their calculator, just come see me at the end of class and I'll help you figure it out. All right, so going back to what we're being asked here, I want everybody to take a second and tell me what my cadmium ion concentration is and my hydroxide ion concentration. All right, so my cadmium ion concentration is just X. All right, so for my cadmium ion, that would be our 1.216 times 10 to the negative 5 molar. Boom. Okay, but my hydroxide ion concentration is not simply X, it is 2X. Right, so again, just make sure to go back and check your ICE table for what it is that you're being asked to solve for. If I'm asked for hydroxide ion concentration, I have to do 2x, so 2.433 times 10 to the negative 5 molar. All right, so again, these are just equilibrium problems. The one thing to kind of remind you of, because it's been a minute, is how we deal with these stoichiometric coefficients that are not just 1, but something greater. All right, so in this case, our hydroxide ions were balanced with a 2 out front. That's going to appear as both an exponent in our equilibrium expression, but also appears in our change box in our ICE table. All right, cool. So let's take this same sort of problem here. Oops. All right, but we're going to take that same 10 grams of cadmium hydroxide, and we're going to try to dissolve it in a solution that contains a concentration of cadmium ions equal to 0.05 molar. Right? So instead of just taking it and dissolving it into plain water, we're going to take it and we're going to dissolve it into a solution that already has some cadmium ions in it. It has a common ion to what we see in our solid here. Okay? So first few steps are going to be the same. We're going to get that same KSP, and I guess I can ask you the same things. What are the concentrations? All right, so let's figure out what is the concentration of hydroxide going to be. All right, so I'm going to do these same first few steps. I'm going to be lazy and just copy and paste, but let me get rid of these colorings here so we're not confused. Okay. So I need my KSP reaction. We're sort of going to make our lives a little bit easier by using the same compound. So we have that same KSP reaction, meaning we have that same KSP expression that we're going to be working with. Okay. Again, we're going to build an ice table. And again, I don't have to keep track of how much solid I started out with. All right, but now in my ice table, what's going to go in that initial box? Take a second and see if you can't fill in this ice table here. All right, so now the big difference is that in my cadmium box, my initial concentration is that 0.05 molar, right? I'm not starting out with none. Now I'm starting out with some cadmium in solution. I still don't have any hydroxide yet. Okay, these are still products, so our concentration is going to go up. All right, and again, if I have for every one cadmium ion that's being produced, I have 2 hydroxide ions being produced. Okay, so now my equilibrium box is 0.05 plus x and 2x. I'm going to turn around and plug these in to our KSP expression. Right, 0.5 plus x, that's my cadmium concentration. 2x is my hydroxide ion concentration. So I get my KSP equals 0.05 plus x, and then in parentheses, 2x squared. Okay, so is x going to be a big number or a little number? Who thinks big number? Raise your hand. Who thinks little number? Raise your hand. Excellent. All right, so x is going to be a really tiny number. So what we get to do is the same assumption that we've used before. 0.05 plus x is basically just going to be 0.05, right? Because that x is going to be so tiny, it's not going to change that number very much. So we get to ignore it in this expression here that just makes our algebra easier. All right, again, you could keep track of it, and all you would find is that it was a waste of your time because you're going to get the same number at the end. Okay? So I need to, again, solve this equation here. We did look up that KSP value. What was it? 7.2 times 10 to the negative 15. All right, so I'm going to divide both sides by that 0.05. I'm going to divide both sides by 4 so that it cancels out. And now in order to get my value for x, I need to take my square root and so x is equal to 1.897 times 10 to the negative 7. Where did this 4 come from? Because it was 2x squared, and that 2x was in parentheses, right? The exponent has to hit that coefficient. That's the biggest mistake that people make. All right, so then finish this off for me. My question was, what is the hydroxide ion concentration? We got our x. Finish off the problem. All right, so how am I going to get my hydroxide ion concentration? I need to look at my hydroxide column on my ice table. That would be 2x. All right, that's my concentration. So 2x is 3.795 times 10 to the negative 7. And what are my units? Big M, molarity. All right, so let's compare the value that we just got from this problem to the value that we got from our previous problem, right? We took that same compound, that cadmium hydroxide. The only difference is in the first problem we put it in water. In the second problem we put it in a solution that contained cadmium ions already. Is the concentration of hydroxide greater or less when we add it to that solution with cadmium ions? 3.795 times 10 to the negative 7 compared with 2.433 times 10 to the negative 5. Which one's a bigger number? 10 to the negative 5 or 10 to the negative 7? Bigger number, 10 to the negative 5, right? Those exponents, negative exponents, are little numbers. So this is the bigger number. All right, so it turns out that if I already have those cadmium ions in there, I'm going to get less of this compound that dissolves. Right? That's just kind of a Le Chatelier's principle argument. We have a special name for this here when we're talking about KSPs. This is what's called the common ion effect. Right? What we found was that cadmium hydroxide was more soluble in water than in a solution containing cadmium ions. That is because that is a common ion to what is in my compound, right? I got cadmium in my cadmium hydroxide. I had cadmium ions in solution, okay? So this is what we call the common ion effect. insoluble compounds are even less soluble in solutions that contain a common ion. All right, so we're learning about these relatively insoluble compounds, right? Which is a little bit of a misnomer because they do dissolve to some extent. But the common ion effect says that these compounds will dissolve or will dissociate even less if there is a common ion in solution. All right, so then the last big thing we want to cover for this particular topic is what's called selective precipitation. All right, let me get rid of this here, clean this up. All right, so we have a solution that contains both chloride ions, a concentration of chloride of 0.05 molar, and sulfate ions, a concentration of sulfate of 0.05 molar. All right, so we're going to start out with this solution that's a mixture of these two anions. Okay. Now we're going to titrate in lead ions. Okay. Chlorides and sulfates are generally soluble. Most chlorides, sodium chloride, for example, most sulfates will readily dissolve in water. We would consider them to be soluble compounds. But lead is a son of a gun, all right? And so it turns out that when paired with lead, both lead chloride and lead sulfate are considered to be insoluble compounds, right? So when I add these lead ions in there, they're going to stick to the chlorides and the sulfates and start to precipitate out, okay? But what I want to know is, first of all, which of my anions will precipitate first? Okay, so my chloride or my sulfate, which one is going to start to precipitate first? Okay, so let's go back to that table and take a look at those values more closely. If we compare these KSP values, which one is less soluble, lead chloride or lead sulfate? Yeah, absolutely, right? Because that KSP value is less, right? A smaller KSP value. This reaction favors the products even less, right? So because of that, because this is the lower number here, that implies that my sulfate will be the one to precipitate out first. Okay? So if I'm going to ask you which one precipitates out first, we're going to compare these two values, figure out which is the more insoluble compound. So in this case, we can say that our sulfate will precipitate first. Okay? So then I can ask, all right, cool, so sulfate precipitates first. What would the lead concentration be when that sulfate precipitates? So now I got to do some math here. All right, so I'm going to need my KSP reaction for this lead sulfate and that KSP expression. Okay, so if I take that lead sulfate, that's what we call a KSP reaction, I dissolve that into solution, I get lead ions and sulfate ions. My KSP expression is then just the product of those two ion concentrations. Okay, so now to solve this, to be clear, this problem is not saying I'm going to take some lead sulfate and put it in water, right? That's not the situation here. In this case, we have sulfate in our solution and we're titrating in lead ions until we get to a certain point that things start to precipitate. So we don't actually have to build an ice table. We already have the variable that we need to solve for, or the variable that we need in order to solve for our lead concentration. We have our sulfate ion concentration already, so we can just plug that into our KSP expression and solve for our lead ion concentration. Okay, we need to go back to that table and grab that value. 1.82 times 10 to the negative 8. Oops. All right, so just rearranging, we get that our lead ion concentration, divide by both sides by 0.05, would be 3.64 times 10 to the negative 7 molar. Okay? All right, cool. So then you're going to take a second and on your own here, you're going to tell me what would the lead ion concentration be when the chloride begins to precipitate out. All right, and let me go back to that page here so that you can get that KSP value for this compound. You're going to need your KSP reaction and expression first. I guess I didn't have to do that. All right, but then you're going to use the value of 1.17 times 10 to the negative 5. All right, so this time in my KSP reaction, I will get 1 lead ion and 2 chloride ions, right? I got to balance that out, which means that when I build my KSP expression, I have my lead ion concentration times my chloride ion concentration squared. All right, again, my initial concentration of chloride was 0.05 molar. So I'm just going to plug that into my KSP expression here. I forgot the value already. 1.17 times 10 to the negative 5. All right, and be careful. That concentration of chloride, that 0.05, needs to be squared because that's our KSP expression. Oops. So we rearrange and solve, and we get a lead ion concentration of 4.68 times 10 to the negative 3. All right, so first of all, take a second and look at these numbers. Does this make sense with what we said at the very beginning, that sulfate will precipitate first? Right? The concentration of lead when sulfate begins to precipitate is 3.64 times 10 to the negative 7. And the concentration of lead when chloride begins to precipitate is 4.68 times 10 to the negative 3. So yeah, our sulfates precipitate first, right? They precipitate at a lower concentration of lead. That concentration then has to climb up in order for the chlorides to start to precipitate as well. Okay, so what we established at the beginning by just comparing those KSP values, that plays out in our math here as well, right? We've supported that. Okay. So then the last thing that I could ask you here about these precipitations would be, what is the concentration of sulfate when chloride begins to precipitate? All right, so what the heck, what am I talking about here? So let's just think about this for a second. We said that we have our mixture here, right? And we're going to start to titrate in lead. That sulfate is going to begin to precipitate first. We'll start precipitating at this low concentration of lead ions here, right? So as it's precipitating, it's being taken out of that solution. Right? It's my concentration, this 0.05, is going to start to decrease as solid lead sulfate is formed. They're not going to be sulfate ions floating around in solution. Now they're trapped in a solid lead sulfate, right? So this 0.05 number is going to decrease as I titrate in those lead ions. Okay? Eventually my lead concentration grows to 4.68 times 10 to the negative 3, and that's when my chloride starts to precipitate. So what I want to know is, okay, well, at that point, how much of those sulfate ions are left in solution? We know that that concentration's been decreasing throughout this titration. As soon as those chloride ions start to precipitate, how much sulfate is left in solution? Okay? So again, we need to go back to our KSP expression for sulfate, for lead sulfate, I guess. Okay, we looked up this value, I don't remember it, 1.82 times 10 to the negative 8. Okay. And what are we trying to solve for here in this KSP expression? Our sulfate ion concentration. Okay. So how are we going to get that? Well, we can get it if we have our lead ion concentration. Do we know our lead ion concentration when chloride begins to precipitate out? Is that what we just calculated? Yeah, right? So I know that when my chloride starts to precipitate, my lead has a concentration of 4.68 times 10 to the negative 3. Right? So I can just plug that into my KSP expression here and solve for my sulfate ion concentration. Right? So lead would be 4.68 times 10 to the negative 3 when those chloride ions begin to precipitate. So that times my sulfate concentration is equal to 1.82 times 10 to the negative 8. Okay, so I'm going to divide both sides by that concentration of lead. All right, we get 3.89 times 10 to the negative 6. My unit should be molar. All right, so again, just to take a step back, and what the heck, what does this number mean, right? We started out with this solution that contained 0.05 moles of chloride and 0.05 moles of sulfate, right? We started titrating in lead. Lead will form these insoluble compounds with both chloride ions and sulfate ions, right? So we'll get a precipitation when that lead combines with these other two ions. Our sulfate will start to precipitate first at a concentration of 3.64 times 10 to the negative 7 molar, right? Very low concentration of lead. All of a sudden, I start to see solid lead sulfate forming, okay? So this concentration will start to decrease, right, as that precipitate forms. Eventually, my lead concentration will climb enough to precipitate out the chloride ions. My lead concentration would have to get all the way up to 4.68 times 10 to the negative 3 for that to happen. Okay? Once that precipitation starts, I can figure out how much sulfate remains in solution. We started out with 0.05 molar sulfate. Now we're down to just 3.89 times 10 to the negative 6 molar, right? We've consumed a lot of that sulfate ion in solution throughout this precipitation. And so at the moment that chloride starts to precipitate, our sulfate has dropped to 3.89 times 10 to the negative 6. Okay? So these are what we call selective precipitation, right? We're selecting one of these two ions in this precipitation to start precipitating first. Okay? And so, yeah, so again, we're going to use those KSP expressions in order to solve these problems as well. Cool? All right, so that does it for chapter 18 here. Again, these are just equilibrium problems. The one thing that I really wanted to stress here is we haven't seen reactions that weren't one-to-one in a minute, right? These coefficients are going to be really important. They appear as exponents in our equilibrium expressions and as coefficients in our ICE table. Cool.